Today we're going to take a look at section 2.2, and it is titled Describing Sets. We're going to have a fair bit of terminology and pieces of things to write down before we get into any actual problems today. So the first thing I want to talk about is what a set is, since the title is Describing Sets. A set is any collection of objects. So you can talk about a set of books. You can talk about a set of contacts in your phone. You can talk about a set of family members, like everybody who lives in your house. Any of those would be sets. Elements are the individual objects in the set. So if you're talking about the books on the bookshelf, it would be the title of one of the books, right? Or one of the books specifically. If you're talking about the contacts in your phone, it would be somebody's name that's in your phone. If you're talking about the people in your house, it would be a person who's in your home. There are two different ways that we talk about describing sets. The first one is called the listing or the roster method. And so if you think about the people in your house, this would be a really good way of describing them. There's probably, somewhere between 2 and 10 people, roughly speaking, in your home, and you could write all their names down. And this would be a reasonable way of listing, right? It's a listing method of all those. Sometimes it's not very reasonable, right? If you wanted to do a way of describing all the students at OBU and you wanted a list of them, that would be a long list, right? Might not be the best way of describing them. But on a listing or a roster method with numbers, let me show you an example so we can compare these two. This would be a set in a roster method. Okay, so there's those curly braces. Some of my curly braces don't end up looking quite right. But this would be all the numbers, 7, 8, 9, ... means we would keep going, of course. And that would be the listing or the roster method for it. Set builder notation works a little bit differently. It looks more like math symbols first. Let me say that. But it minimizes the amount of writing if you were writing larger numbers. Like this is fine, 7, 8, 9, but what if we wanted 10,000, 10,001, 10,002? The more writing becomes messier. So this is actually, in many cases, a more concise way of doing it, but it looks a little funny. So first of all, just write down what I have, and then I'll explain what we've written, okay? So you start out with the curly brace, just like before. You're going to put, it doesn't really matter what letter it is. I tend to use X. Sometimes your book will use N's. And a vertical line. And then I'm going to write X is greater than or equal to 7. And again, I promise I'll explain what all these symbols are in a minute. There's an X. There's this sort of curly E-ish looking thing. Definitely needs to be curly. All right? It's a symbol that has a mathematical meaning behind it. You don't get to just decide you want it to be a boxy E. It doesn't work like that. And then you're going to put an N that has 2 lines on the left and a curly brace at the end. Okay. So think about when you were in maybe an algebra class in high school and you had numerators and denominators and radicals and less than or equal to signs and all this kind of stuff, right? So if you gave that to one of the children that you guys see sometimes in the schools in second grade, they wouldn't know how to read that, right? But you know how to read it because you've done it. You've worked your way up to being able to handle all the symbols. This is the same idea. These are foreign symbols to you, some of them, but there's nothing complicated about it, and I'm going to explain each of the symbols, okay? So the variable at the front is just telling you that it's all of the values, right, that have the following characteristics. So we read this as X, and then the vertical bar is read as such that. So it's all the values where the next things are going to be true. You're familiar with the inequality piece. X is greater than or equal to 7. You'll have no problem with that one, right? You've seen that for a long time, since middle school at least. What comes after that is actually telling you what kind of a number we're talking about. So that N is the natural numbers. Okay, so I'm going to talk more about the number system on the next slide, but the natural numbers is where we begin when we're first learning to count as small children. You start with the number 1, right? 1, 2, 3, 4. And if I talked to my 6-year-old, she would understand those numbers. As soon as I introduce other kinds of numbers, she's going to have a glazed over look, and she's going to think I'm a little bit crazy, right? She doesn't know anything about negative numbers yet. She's not talking about decimals or fractions. So this is a way for us to say what kind of numbers we're working with. So 7.5 is not sort of a part of this description, right? I mean, 7.5 is greater than 7, but it's not a natural number. So that's why there's two pieces in this description. One piece is telling you where it starts or ends, right? And the other piece is telling you what kinds of numbers you're working with. So if I read this from left to right, like you would have read an equation in Algebra 2 or something like that, I read all x such that x is greater than or equal to 7 and x is a natural number. Now, this symbol right here, kind of skipped over that. This is the symbol that means is an element of, okay? And we'll put that on the next slide as well. So it just means it is one of these things. It comes from that group. Comes from the set or the grouping of natural numbers. And that's where we'll start on our next slide. So some symbols that we need to be aware of. The first one I already mentioned, was the element symbol. So this curly one, and it is curly, right, means is an element of. So what do you suppose would happen if I do that curly symbol, curly E, and I draw a line through it? Yeah, it means it's not an element of, just like if we do equals and not equals. So is not an element of. Okay, the second one we've already dealt with as well. It's the N with the two lines on the left. Oh, I didn't address why there's two lines on the left. So all of our symbols that I'm going to write down for the number systems are always going to have double lines somewhere in the symbol. If you actually see it in print, like in your book, it may not even look like the double line, but what it will look like usually is it will have a thicker line. Like it will bolden it, so it'll look something like this. That's what you see when it's in like texted typed print, okay? But I'm not going to shade in my double line. I'm just double lining it. It's easier to write it that way if we're going to write it out. So this means, like we said, the natural numbers. Natural numbers are also sometimes called the counting numbers. And like we said, these are the numbers where we start with 1 and go up from there. So somewhere along the way, somebody introduces the idea of the number 0, right? Somewhere when you usually hit subtraction is when that will often happen. And you talk about what happens when you are working with something that doesn't have any values, like I don't have any bananas in my bag, right? There's 0. And so we actually call that, we'll do a W, the whole numbers. The whole numbers are very similar to the natural numbers. They just throw in the number 0. So you start, that's terrible. Let me try that again. 0, 1, 2, 3, and so on. So we don't add a lot. We added just a little bit of something. But I don't know about you, but I actually remember being in a bus, I think, when somebody did something to me like this. He said, well, what's 3 minus 6? And I was really little, obviously, because I was like, well, you can't do that. You can't do that, right? That doesn't make sense. But of course you know better right now, and I know better now. And when we do that, we actually have to introduce another type of number. So the type of number we're talking about right now is called integers. The proper symbol for integers is a Z. Sometimes this particular book likes to use the I. I is not a very good symbol. Yes, I recognize that integer starts with I, but so does irrational, and so does imaginary. So most resources don't use I's for any of them because it could mean more than one thing, and so just avoid that. Z is actually, I don't know what the word is, I should look it up at some point, but it's actually the Latin word meaning integers. That's where the Z comes from. So this is integers. And your integers are your positive and your negative whole numbers. So we start with the dot, 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 and then we're going to put the -3, -2, -1, and then we keep going. 0, 1, 2, 3, and we'll go on from there. It's the positive and negative whole numbers. If we expand our number system a little bit, in fact, sometimes kids will encounter the next one before they even encounter integers. Integers are usually introduced in about 5th grade, by the way. So my 5th graders right now still haven't quite got there, my personal children. But I know it's coming. It's like on the horizon. But they're already working with fractions, okay? So fractions sometimes occur before integers occur, but they're still only working with positive fractions. So, because they haven't started with negative numbers. So if you do a Q with a line on the left like that, this is rational numbers. And there's not a good way to write this down in a listing method. There's not even a great way to write it down in a set builder notation method. So what I'm going to do is I'm going to put a curly brace and I'm going to put just a description inside. And the description is that it can be written as a fraction of integers. So 2/3. Numbers that look like decimals, 3.4. I know this is not this class, but you guys know from previous experience you can take the number 3.4 and you can find a fraction that goes along with that, right? Yeah. It's true for the whole numbers too, right? If I have the number 5, 5 can be written as 5/1, so I'm good to go. It's a rational number. The reason it's a Q is because Q comes from the word quotient. Quotient has to do with this idea of division, right? Numerator divided by denominator, and that's what a fraction is. So you're getting a quotient. That's why there's a Q there. And then the last one is real numbers, and that's where you actually use the R. So these are for real numbers. And real numbers include all rational. That's everything we just talked about above. And irrational. Numbers. And irrational numbers are decimals that don't ever end or repeat. So you know some of them very well, like pi. You've been working with pi since middle school at least, right? You might have encountered the number e in a higher level math course somewhere in high school. You've definitely encountered things like square root of 2, right? Those are all examples of irrational numbers. So if we take all that kind of a number with all the kinds of numbers that we already talked about where we can write them as fractions of integers, all that combined together makes the real number system. All right, so are you ready to get to an example? There's a lot of background information. Sorry about that. All right, so this one is actually going to give us a description. And we're going to write out both the set builder method and the listing method for the description it gives us. So the first one says, write the set of all natural numbers less than 5. And we're going to first use the listing or roster method. So with the listing or roster method, we just start with a curly brace. And we either start with the highest or lowest if there's a value to start with. Here, the lowest because it says bigger than 5. It says less than 5. So it says less than 5 and it says natural number. So what is the smallest natural number that is less than 5? 1. So we're starting with 1. And what will we end with? 4, right? Because it said less than 5, not less than or equal to. So the roster method is actually really nice for this particular set. It's great. 1, 2, 3, 4, super easy. So this is not a best example of the next one. We can do it, but it's like, trying to kill the fly with a sledgehammer, right? I mean, it's way overkill, all right? So I understand that. You're looking at, well, why would I do that? Well, you're doing it right now because it's my example. That's the why. But there's other cases where it's actually a much better solution. So for this one, you start with the curly brace. It always starts out the same way. You can pick whatever letter you want. We'll just pick a different one just for fun right now. So I told you N is another one we sometimes will use. So I'll use N. If you want to use X, use X. And then you do that vertical line. So this is N such that. And it really doesn't matter what order comes next. I usually do the inequality first. So this one says that N is less than 5, right? So whatever letter you chose, less than 5. So one piece is the inequality, and the other piece is the type of number. What type of number are we working with? Naturals. So we do N. We write that element symbol. and then we write the natural numbers and close off our bracketing. All n such that n is less than 5 and n is a natural number. You could switch these two. It doesn't hurt anything if you do. If you want to talk about the natural numbers before you talk about the inequality, be my guest. But both pieces need to be there somewhere. Okay? Any questions on that? All right. A little bit more background. Two of them are on this page and one of them you'll have to flip your page for. The first one is equal sets. Equal sets are two sets that contain exactly the same elements. So if I talk about my family, as in the people I live with, and my husband talks about his family, as in the people he lives with, we're talking about the same people. Those are equal sets. Okay? Exactly the same elements. A one-to-one correspondence is where you pair things up. And when they pair up perfectly, you know, like everybody has a partner, that's called one-to-one correspondence. They have to match exactly. So this is always what I enjoyed when I was a child. My mother had a friend who had 3 daughters. And in our family, we had 3 kids as well, 2 girls and a boy. So when we got together, everybody had a playmate, right? It was a one-to-one correspondence. It worked out perfectly. Now, if you have a one-to-one correspondence, like my mom's kids and my mom's friends' kids, right, my friends, then those are actually equivalent sets. This is one of those unfortunate English issues because we use the words equivalent and equal as though they mean the same thing when we're speaking in our English stuff, right? And here they don't. Here, equivalent sets are sets for which there exists a one-to-one correspondence between the sets, i.e. they have the same number of elements. Everybody can be paired up. All right, so oftentimes there's a natural pairing that makes sense. My example, right, the oldest kids hung out together and the middle kids hung out together and the youngest kids, that was the natural sort of pairing. But of course, that's not the only way the pairing could have occurred, right? What if in those arrangements there had been certain boy-girl combinations? So the boys wanted to hang out together and the girls wanted to hang out together, right? Or if for some reason the oldest girl over here really got along really well with the youngest girl over there. There's other correspondences that are possible. So there's not just one way that you can pair these things up. And that's what this one is actually talking about. If I had 6 elements in each group, so let's say I had 6 people in my family. I have more than that, but let's pretend. I have 6 people in my family, and we go over to somebody else's house, and they have 6 people in their family. And we want to do some sort of a pairing things up. How many ways can I make that happen? Okay? So let's say, for instance, we'll do a slightly different example. Let's say that I had one of those, I can't remember what they call them, but you see them on TV. You know those things where the speed dating. You guys seen speed dating before? Y'all know what I'm talking about, right? So let's say we have speed dating and there's 6 guys and there's 6 girls. And the question is, how many, sort of individual conversations do you have to have for every guy to talk with every girl? All right, that's what we would actually be counting up. How many ways can I do this pairing so that I can figure out how much time this is going to take? All right, I'm reserving the room. I need to know how long it's going to take to pair these people up and get them all talk. So if you imagine the first person that comes in. So imagine there's 6 gentlemen standing in the room. The lady comes in, and the lady has to pair up with one of them. How many choices does she have? She has 6, right? She has 6 choices for the first person she could talk to. But then, actually, let me just put a line here. But then, once that pairing has been happens. Once that pairing happens, how many choices does the next young lady coming in have to pair up with? 5. She only has 5 options for the person that she's going to go on a date with or whatever, I don't know. What about the next person that comes in? Young lady number 3. 4 choices. And 3, and then 2, and then there's 1. Poor last girl, she has no choices. All right, and we'll talk about, I think it may be later in this lesson, or maybe it's the next one. what we actually do is we multiply each of these for how many times we would need this to be. So if we multiply this, we will actually have the total number of pairings that could exist among these 6 gentlemen and 6 ladies. 6 times 5 times 4 times 3 times 2 times 1, and what do you get? Did anybody multiply that? Nobody has a calculator today? I see a calculator sitting on desk. Somebody multiply for me. What do you have?
96.
What?
Is it 96?
Nope, I think that's too big, but you're close.
Is it 720?
720, yeah. 720. There are 720 possible correspondences. $720 pairings, if you wish. Right? I mean, like each individual girl only has 6 choices, but because they all have choices, this gets fixated. Now, there's going to be an example in your group work, which isn't going to happen today, it'll happen on Friday, but when you get to the group work, where some of these things are going to be fixed. Like they're going to say, but person 1, they're not going to use people, but I'm going to use it right now. Let's say these 6 gentlemen and these 6 ladies come, but all of a sudden you realize that 2 of them have already met each other, and that's absolutely not going to work. They don't like each other, right? Or 2 of them have met each other, and they're already dating. Now, why they showed up for the dating event, I don't know, but just pretend with me. Or 2 of them showed up and they're married, right? We got a problem, but you can see how it would change the numbers, right? They don't have any choices anymore. So, we show up at an event, and, I'm already married. I'm going home with my husband, right? I'm not going home with some other random guy, right? So that actually isolates how many choices that we have as we're working our way through. And so there's going to be some examples in your homework where it says you've got like the letters X, Y, Z and the numbers 1, 2, 3. But if X has to go with number 1, they only get 1 choice. And then the number of choices decreases for everyone else after that. Are you with me? So there's going to be some caveats to this as you work your way through. All right. Cardinal numbers. Very fancy word for just saying it's the number of items in the set S. It is written, and it looks kind of like algebra. You do an N, and you do a parenthesis, and then in the set S. And all this is really saying is it's the number of items in set S. How many of them are there? So if I were to do my family, right, the number of items my family is and those who are living in my home would equal 8. So this isn't equal to the set itself, it's just the number of things that are in the set. We could talk about the number of items that are currently in your inbox for your email, right? It's a number. A finite set is a set for which the cardinal number is a whole number, right? It's 52, it's 768, it's 2,497. Okay, it has a fixed number. And an infinite set is a set for which the cardinal numbers is not a whole number. Okay, I think you guys have an idea of what we mean when we say infinity. It just continues to sort of increase forever or continue on forever. It's what happens when, so my youngest daughter and I have this thing, and she says, I love you, and I say, I love you too, and she says, I love you more, and I say, I love you most, and she says, I love you to infinity, and you guys know what comes next, right? I love you to infinity and beyond, right? Buzz Lightyear. So, but I put this out on Facebook because it's just this cute thing we do, and one of my friends who's a math teacher, a middle school math teacher, she said, but really, can you love beyond infinity? Because infinity is already infinite, right? It's already there. So she says, I think Buzz Lightyear got it all wrong. So that's infinite. And the last one here is the most boring thing ever. It's the empty or null set. And it's a set that contains nothing, has nothing in it. Cardinality of 0, right? Because there's nothing in it. And it has three different ways it can be written. 2 different ways it can be written, and one that it can't. That's what I meant to say, okay? So you can write a 0 with a slash through it. Okay, so for those of you who like to write your zeros already with slashes through it, please stop. Got on to my 10th grader about that the other day. I was like, honey, please do not write your zeros with slashes through it. She's like, why not? And I'm like, I promise you it's going to be a problem later on, especially for her because she's going to do more math. She wants to do more math. And this symbol comes up again. So this is a symbol that does not mean 0. It means it's a symbol for the set with nothing in it. The other one, which I kind of like even better, is simply brackets that have nothing in them. They're so apparently like exactly what they are. They're empty. It's an empty set, right? Okay, so I'm going to write down now what you can't write down, and then I want to make sure you put a big old X through it, just like I am, okay? You do not get to do this with this around it. This is a no-no. I feel like I should make the X red. We're going to make an X red. No. Do not pass go. Do not collect $200. No, no, no. All right? Because that's actually a set with the empty set inside of it. I mean, it's a dreadfully stupid set, right? But it's actually got something in it, namely the empty set in it. We don't want to do that. It's never going to be useful, okay? So one of the other two will work. All right, we'll come back to the idea of empty set next class period a little bit. But let's keep moving, talking about cardinal numbers of some other kinds of sets. So this one says we're going to find the cardinal number. Remember, cardinal number means the number of items in each set. And for the purposes of what we're doing, these have the lowercase letters at the beginning, like part A, part B, part C, so forth. I'm just going to call this set A. I'm going to call this set B. I'm going to call this set C. And call this set D. These are our sets. Now we've done some things with counting methods already. Back in section 1.2, when we were, or 1.1 rather, when we were looking at Gauss's method. Do you guys remember that? Where we looked at the number at the end, we subtracted some number at the beginning, and we had to divide if it skip counted. Remember that? We're going to use that again here. So the first thing is to do the symbol. So it says the number of items in set A. So it's N of A. And then we're trying to figure out, well, how many of them do I have? So this is the numbers from 9 to 99. And I'm not skipping anything. So how many of these do I have? How many numbers are there? Is it 90? Really close.
91.
It's 91. So why is it 91 and not 90?
Because you subtract 8 and 9.
Right. So we're going to subtract the number in front of the number we begin with. So what we're doing here really is 99 minus the 8. That is the number that comes before the numbers in my set. And we talked before about one of the ways to think about this is that there's 99 items from 1 to 99, right? And I don't have the first 8. That's why I'm removing the first 8. And of course, like you said, that ends up being 91. So my cardinal number for the first one is 91. Okay, how about the second one? We are skip counting now. These are only even numbers from 2 to 2002. What do you think?
Whatever it is, you're going to divide it by 2.
Whatever it is, we're going to divide by 2. Does everybody agree? Because we've only got half the numbers, exactly, every other one. So what do you think we're going to divide by 2? 2002, that's right. If all the numbers were there, including the odds that are missing right now, that would be 2002 numbers, right, from 1 to 2002, and then I'm splitting it in half because I only have the evens. So this gives me 1001. Okay, C looks way scarier than it really is, okay? This is set notation, which we're still getting used to, I realize. This set, if I were to write it out, is the set of squares, right? It's x squareds. And it's telling you what the x values themselves are. They're 1, 3, 5, 7, and so forth. So if I were actually wanting to know what does this set look like, well, it looks like 1 squared, 3 squared, 5 squared, up to 99 squared. That's what the items, the elements in the set really look like. That's not really what I'm asked for, but I just want you to understand what we're actually describing here for the moment. What we're asked for is how many of them are there? hopefully as you're looking at it, you're saying, does the squared matter? And the answer is no. The squared doesn't affect anything in terms of how many of them there are. However many of them there are from 1 to 99 is exactly the same number as there are from 1 squared to 99 squared. Are you with me? It's okay? So how many numbers are there from 1 to 99? Okay, so 99. What's next? Because it's every other one as well, right? So we are going to have something to do with this. If I do this, I'm going to have a problem. Why am I going to have a problem? I'm not going to get a whole number, right? 99 divided by 2 does not give me a whole number, and there's definitely a whole number of numbers, right? I don't have half of a number somewhere hanging out, like, half of an erased 2 or something like that. That's not what's going on here. So what's missing to give me the whole number here? Because I'm not just going to do this and then round something. That's not what we're trying to do. Do you remember how we approach this? What did we do on the very first one on this page, where it started with 9 and it went to 99?
We started with the letter. Well, the value that was supposed to come before the first value.
The value that came before the first value, what did we do with it? We subtracted it. So what's the value that becomes before our first value here? It's actually -1, right? So if I were to sort of go backwards here in this list, the value that I would get before the numbers began, right, in the pattern would be -1. So over here, I'm going to subtract -1. I'm going to tell you another way to think about this here in a minute, but this is a very concrete way of always doing the problem. You can always take the number at the end minus the number that comes before your number and then divide by the common difference. Is what's really you're dividing by. You're dividing by the common difference. So what is 99 minus -1? It is 100, and 100 divided by 2 would give me 50. So the other way that you could think about this particular one, this doesn't work for all numbers, but if you're taking the numbers from 1 to 99, it's really just the numbers from 1 to 100, and it's the even, or the odd ones instead of the even ones, right? It's half the numbers between 1 and 100. Well, that's 50 numbers. So you can also reason through it sort of in a more general way in that fashion as well. There are 50 of these. Okay, the last one says that we're looking for all x such that x is equal to x plus 1 and x is a natural number. So we have to make this equation true. So can you give me an example of a number that makes this equation true? One. So if x is 1, is my equation true? Not going to work, right? So that one didn't work. Can you give me a number that makes it true? Okay. Let me talk about 0, a couple things here. First, let's see if 0 makes it true. Does 0 make it true? No. Even if it did, it's not allowed. Do you know why it's not allowed? Because it's not a natural number. So it fails actually on both conditions.
Would it be a negative?
Okay, so again, even if a negative number works, it fails because I'm only looking at natural numbers. A negative number won't work either, by the way. So the conclusion is there aren't any, right? Well, think about that. Y'all know that to be true. There's no number that you can add 1 to and it doesn't change it.
You just think about real life. You
Yeah.
never add something to something.
Right. I don't add an apple to, my lunch bag and my lunch bag remained the same, right? Somehow it changed. So you can't add something that's not 0. This is the number 1. and it not change something. So over here, this is a cardinality of 0. What that actually means is that this set D, this is not the question, but this is the empty set, right? That's what it is. I just created, or didn't create it, but we just talked about a set with a cardinality of 0, or an empty set. Okay, let's fill in the last, 5 blanks or whatever on this side of the page, and then we'll stop. Venn diagrams, which is what we'll pick up on next time. Venn diagrams are diagrams used to illustrate ideas and logic. So this is a picture, it's a diagram. A universal set is the set that contains all the elements that are being considered. And a complement is if you're given a set F, it's all the elements in the universal set that are not in set F. And in this book, they write it with a bar on top. Okay? If any of you took contemporary math with me during a J term, that book writes it differently. Sometimes that book, or the other books will write it with a prime, or they'll write it with a little C up here in the air. Okay? So I will draw you pictures of Venn diagrams, and we'll do lots of things with Venn diagrams as we continue through this section, and we'll pick up right there next time when we come back on Friday.